Okay, so let's continue this problem. The first thing we need to determine is the pressure and temperature at the end of the heat addition process. So again, it doesn't say T3, P3 per se, but it says the end of the heat addition process. So we know it's T3, right? Because the heat addition process is this guy here, and therefore we know that the end of the heat addition process is when we reach that end state there, which is state 3. Okay, so to be able to find T3 and P3, we're going to use two things to our advantage. One of them is that we know that this is an isovolumetric transformation from here to here, so there's no delta V. And the other thing is precisely the ideas behind the first law of thermodynamics. Okay, so let's have a look here. This guy is an ideal gas, and therefore we're treating air as an ideal gas, I should say, right? Because we're using the ideal gas tables. If we were not treating it as an ideal gas, we couldn't do anything we did so far. So if it's an ideal gas, it respects the relationship PV equals nRT, and we can use that relationship as P specific volume V equals over T1 equals PV2 T2, right? It's making everything. So we're doing PV equals mRT, and then we're doing P specific V equals RT, because volume over mass is specific volume, so therefore P specific V over T equals a constant. So regardless of what we do, it's always going to be a constant, and therefore we can make sure that no matter which state we're in, it's always going to be there, right? Now, the other thing we know is that from 2 to 3, there's no change in volume. So we're going to use those two things to solve this. All right, first thing I want to do is find what is my P2, right? So for now I only have my T2, 773, that we grabbed before by interpolation. But my P2 I still don't have, I don't know the pressure to. Okay, so I'm going to use PV equals nRT, and I'm going to use it for state 1 and state 2. Okay, and you'll notice that we have everything we need. We have the pressure 1, that's 95 kilopascals. We found the temperature 2 from the interpolation. We had the temperature 1 since the start. What we don't have is volume 1 and volume 2. So we don't have V1 and we don't have V2, right? But we do know the ratio between them, right? It's been given us from the start. So that's going to be the maximum volume over the minimum volume. So that ratio is 8. Right? That's the ratio that we were given in the beginning. We knew that from the start. So we can put 8 in there, and we're going to grab that the P2, pressure 2, is 1,700 kilopascals. Right? So now we have P2, and I'm going to go and repeat once again. I'm going to repeat once again the same equation here, but now I'm going to do from state 2 to state 3. Right? So let's go ahead and zoom in here. Okay, so again, doing the same relationship, but now for P2 and P3, and we know that volume 1 and volume 2 and 3 are the same, right? It's an isovolumetric process, so these guys are the same. I can divide by them, they go away, and we're left only with the relationship between the pressures and the temperatures. Okay, so P3, which is one of the things we want to determine, P3 equals P2, which we have, times T3, which we don't have yet, divided by T2. Right, so for us to find the pressure on 3, we first need to find the temperature on 3. Right, so we're just going to leave this guy on pause for now. Let's go find the temperature 3. To find temperature 3, what I'm going to do is take advantage of the fact that we know how much energy is going into the system from 2 to 3, right? That's Qin. So from 2 to 3, let's bring it to the middle here. From 2 to 3, there's no change in volume, isovolumetric. If there's no change in volume, we know there's no work involved in this operation. So if this process doesn't have any work, our first law of thermodynamics says the following, right? Delta U equals work plus any Q. In this case, work is 0, so our delta U, which in this case is final state minus initial, 3 minus 2, equals our Qin, which is the only energy that's going in to our system, right? So check out what we have here. We know U2. Remember I grabbed that from the interpolation, the same place I grabbed the temperature to. I know Q in, 750, so I can just sum these two guys up and grab my U3. And once I have U3, I've defined pretty much the third state, right? Because then, if you remember, I can grab temperature, I can grab internal energy, I have internal energy, I can grab temperature, I can grab VR3, I can grab PR3, I can grab entropy and so forth, right? So I can use this guy to find all these properties that are related to temperature. Okay, so now let's first grab T3, which is what we're after. From the table, I can use this information to go straight to the table. So I go with U3, go to table A17, and I have a copy pasted the table here. Okay, so we have the temperature here on this left column. We have internal energy on this column here. And what I did, I just interpolated, because we know that our internal energy U3 is the 1200. So I interpolated that for temperature, and I grabbed the T3. So my T3 is 1539. Okay, and as you can expect, what I did already as well is grab my relative specific volume 3, because I'm going to use that to be able to solve for 4, right? Because we know from 3 to 4 it's a nice entropic process. Okay, so I already grabbed that ahead of time. But now what I'm going to do is I'm going to take this V3 that we just found, and I'm going to, T3 that we just found, and I'm going to go and plug it back into our P3 equation so that we can solve for P3. Right, let's just follow this red line here. So there you go, right? We were missing, if you guys recall, we were missing T3. Now we have it, and I've just plugged it in there, and therefore I grabbed my P3. So we just solved part A of the problem. We now have the temperature 3 and the pressure 3. Okay, brilliant. So now let's move on to the next part. What does the next part ask of us? Let me just check. The network output. Okay, network output. That's easy because we have a cycle, right? So if we have a cycle, what does that mean? It means that when we're going from one to the other, we're going from here you go. When we're going from state 1 all the way around the cycle and back to state 1, our delta U is 0. Right? Let's think about it for a second. If my internal energy at state 1 is 50 kilojoules, once I go around the cycle and go back to state 1, if I'm back to state 1, it's 50 again. So 50 minus 50, that's 0. So my delta U for any cycle, when I do the whole cycle, is always going to be 0. Right? I can take advantage of that, because if my delta U is 0, this guy goes to 0, and then I know that my work has to be equal to any change in heat. All right? So that's why we looked at that graph in the first part of the video, in which we saw how much work was being done by the area. So check it out. Because delta U is 0, that means that my work equals my delta Q. Now there's two options here, right? Either this is going to be positive or negative. Let's think about that. Because either we're going to have more energy coming in than going away, or vice versa. So if my energy going out is greater than my energy going in, then I have to actually give more work to the system than I can take away, right? So for this to be valid, for this to be true, that means that I have to input work for this for us not to violate the first law of thermodynamics, because I can't create energy, destroy energy, right? If, however, my Q in is greater than my Q out, that is, I'm putting more energy than I'm rejecting in the form of heat, then I actually can get a work output. Okay, and then let's just think about this in a real life example. If we have a car, right? If the amount of gasoline you put into the car, of petrol, is less than what it's expelling as heat, either through the exhaust or through the wheels or anything like that, the engine, then we're not going to have any energy left to move the car, right? If, however, the amount of petrol that I put into my car is greater than what I'm losing due to heat, then the leftover energy is the energy I'm going to use to actually drive my car around, that I'm going to get as useful work, right? So the first case we're not going to see unless we have a defective cycle, something that has been poorly designed, but we should not expect to see this in any of our problems, right? Okay, so now that means that my work out equals my Q in minus my Q out. I know Q in, right? I have known this from the start. This is the 750. But I don't know Q out yet, because I can find Q out, right? Remember where Q out is? Q out is on the last part of the process when we go from, so it's when you go from state 4 down to state 1. Yeah, and this is where my Q goes out. That's my heat rejection part. So as long as I can find the information for state 4, I can use that information to relate Q out. Okay, so from 4 to 1, again, delta V is 0, right? Just like 2 to 3. So therefore, again, my work is 0. If my work is 0, that means that delta U equals my Q. And I can use this relationship to find and define my state 4, right? Because what's the end state? What's my delta U? My end state is 1, so U1 minus U4 has to be equal to my Q out, which is what I'm looking for. Okay, problem is I don't have U4 yet. U1 I have had from the start. If you guys recall, I did it in green. Right in the very beginning of the first video, I grabbed U1 because I had the state defined completely. So all I need is U4 to be able to find my Q out. Okay, and that's the interesting part, right? Because we can use state 3 to find state 4. Remember I mentioned it's an isentropic process, so therefore it's we can use the relationship between the relative volumes. So my max over my minimum, we know that's 8 all along. We always knew this. So long as I have this guy, I can find this guy. And I do have this guy. Remember, I grabbed it from the table. Let's go back for me to show you guys. I grabbed it from the table. From the same time I grabbed my T3 over here, I've went ahead and grabbed my VR3 as well. Okay, so I have that information. I can calculate my VR4. With my VR4, I can calculate my U4. With my U4, I can calculate Q out. Okay, so VR4 will be 8 times VR3, which is going to be 52. I can use that information to go to the table A17 again and look for VR of 52.7. Then I can grab temperature 4. Not going to need it per se at the moment, but I've grabbed it. You'll see why later. And I grabbed U4, which is what we're looking for in this very instance. Okay, so I can go back to where we were, plug in U4, and then find what we're looking for. So there you go. U4, U1 minus U4 equals Q out. So that's going to be 214 minus 50, 571. So my Q out is 357.6. Now mind the negative sign, right? As usual, the negative is indicating what is happening with this energy. And the negative in this case is telling you it's going away from the cycle. Now, we know it's going away. We've known that from the start. From 4 to 1, we have a heat rejection process. So if you want to think of this as just the magnitude of the heat that you're finding, up to you, right? As long as you're saying here Q out, that's the same thing as putting the negative there. Okay, so if you guys recall, we wanted Q out because we wanted to find the work, right? So let's go one step back again. Boom, right? We wanted work, and to find work, we needed Q out, because work is just going to be the difference between Q out and Q in. Now we have both. We have 750 for this guy and 300 something for this guy. So let's just subtract them. I have 750 going in, and I have 357 going out, right? So first law of thermodynamics says that the difference is what I have as work, because we can't destroy energy, right? Cool. So that's the answer for part B. Let's go to part C now. Part C is the easiest one. It asks us to what is the efficiency of this particular cycle. Well, the efficiency is how much did I get as an output in relationship to how much did I have to start with, right? So how much did I get as an output according to how much did I actually have to use an output, right? So if I didn't reject any heat whatsoever, it would be 100%. But since I did reject some, it's going to be less than that. So let's do the math. Part C. Output over the supplied one, right? What is our output? Our work. What is supplied? Q in, right? That's the fuel that we're putting into our system. That's a battery for our car, battery for your cell phone, right? We have those values. Q workout was 392, Q in is 750, so this particular cycle has an efficiency of 52.3%. Okay, brilliant. Part 4. Part 4 asks us to calculate the mean effective pressure. Mean effective pressure. What the hell is that guy? Well, the mean effective pressure, as the name says, it's a mean pressure. Okay, so the idea behind this is, if you guys recall, the way that work is defined is the integral of P, pressure, dV, from 1 to 2, in our case from 1 to 1, right? From 1 to 1 because it's a full cycle. Okay, and then pressure varies with volume, right? So as the volume is changing, my pressure is also changing. So this guy is actually a function that's changing with volume, so I can't remove of the integral. So my mean effective pressure is, if I imagine the following, okay, what will be the pressure that I could remove from this integral, and it will still give out the same answer. So what will be the mean pressure that I could use that would be equivalent to integrating this whole thing over the whole cycle? Okay, so by definition, what I'm saying is that the work is going to be equal to that pressure times the integral of only dV. Because if it's a constant, if it's a mean that does not change, that means I can remove from the integral, and therefore I'm just left with the integral of dV, which is just delta V, right? How volume changes in the cycle. Okay, so if I want to calculate my mean effective pressure, just rearranging and have that, that's going to be my work divided by my change in volume. I have known my work from the start, that, and this guy is 392.4, and that's kilojoules per kilogram, if you guys recall. So what I need is to find my delta V, because I don't have that yet. Okay, and if I can grab this in meters cubed per kilogram, I can remove the kilograms from this, and I can be left with kilopascals, right? That's going to be kilojoules over meters cubed. So for us to solve this, we're going to have to find the two specific volumes. What two specific? Well, there's only two volumes in this whole problem, right? There's only two volumes throughout the whole cycle. Volume 1 and 4, which are the same, and volume 2 and 3, which are the same. So I need to grab these two guys, subtract them to find what is my delta V throughout the cycle. How are we going to do that? Ideal gas equation. Okay, so let's find my delta V. P1 V1 equals MRT1. This is the best state because we have it all defined from the start. So what I'm going to do is I'm sending this mass dividing over here. So I'm going to have V volume 1 over mass. That's going to be a specific volume, right? Will be equal to RT1 P1. We know everything, right? R is going to be my ideal gas constant, specifically for air. Then T1 we have, and P1 we had from the start. So the R we already grabbed from the table, we did that before, right? So I just copy pasted table A2 here. That's the R for air just there. Okay, let's just double check on the units of what we're doing. We have R, temperature and pressure, so kilojoules per kilogram Kelvin is R, my temperature in Kelvin, and my pressure in kilopascals. So my Kelvin cuts my Kelvin, then I can transform my kilojoules into kilopascals times meters cubed. Kilopascals go away, so what I'm calculating is indeed meters cubed per kilogram, which is specific volume, right? So solving that math, I get 0.9, and this is my V1, right? So that's the greater volume, so that max volume. So now let's find the volume minimum, which is V2 or V4. V2 or V3. You can choose either one. We have more information. We have information for both, right? So we can do either. So check it out. Again, same thing. I divided by the mass, so R, T2, P2. The R is the same. T2 we have, P2 we have, and we calculate that's be 0.1133 meters cubed per kilogram. So indeed smaller than V1 as we would expect, right? So now we have the two volumes so that we can calculate the difference. I'll suggest you guys can go ahead and check using V3, right? V3 has to be exactly the same as V2. So you can plug in the numbers for this equation here, but instead of using T2, use T3 that we have already, and instead of using P2, use P3 that we have too. All right, so now we have both volumes. We can go back to our mean effective pressure equation, which was what we're trying to do from the start. Remember, we were missing this guy. Now we have this guy. Let's go ahead and plug it in. My mean effective pressure will be the work divided by the difference in volume, which is 0.9 minus 0.11. So don't forget that we just checked the units, and that's going to be given in kilopascals, right? So kilograms goes away, and I got 495 kilopascals. What does that mean? It means that if I use 495 kilopascals, this is equivalent to having a mean pressure that will be integrated from throughout the whole cycle, right? In spite of my pressure varying, varies quite a lot. If you guys recall, it goes from 95 all the way to, I think it's 1300 on P3. If I use 495, that's going to be a mean pressure that's equivalent for the whole cycle. Okay, so that's it for this question. Make sure to solve it on your own. It's a big question. It involves a lot of concepts we'll be talking about from now on. Right, hit me up if you have questions, and I'll talk soon in the class.